Okay, so series, and this a couple tables is crucial to understanding series, and especially the very common confusion between series, sequences, and series. Okay, so sequences produce a series, but it's not a sequence. Okay, so when you start adding things, adding the terms of the sequence, that's how you create a series. You create a new sequence, and the limit of that sequence is the sum of the series. So it's that notation is slightly misleading. This notation for a sequence. What the hell happened here? Again, I'm referring to this. Okay, so it is a very abbreviated notation for the idea that is fairly large. It has some build-up in it. Okay, so as you can see, once again, there is a sequence to begin with here, and then you create a new sequence. That's a new sequence, and then you take the limit of that sequence. Okay, so that's the what we're talking about. So the sequence A in itself has a limit. That is irrelevant. At least for the time being, we're looking for the limit of another sequence, and that's the sequence is specifically a sequence of partial sums. So recursively, we keep adding those elements, and that creates a new sequence, and its limit is called the sum of the series. Okay, so the series is a sequence of partial sums technically. So especially it is revealing if you look at these tables at the bottom. So in black is the sequence, so that is the discussion that we had previously in mid-semester of sequences, and as you can see, you can treat them numerically. You can have a formula, you can have n goes to infinity, where does the sequence goes, and where does it go? Both of the sequences happen to go to 0, and now what we are adding to this discussion is what we really care about, new stuff. We create partial sums. So every time we add an extra element as we move down, we add an extra element, the one that we see on the left. So from 1 to 1 plus 1/2, then to that you add 1/3, then you add to that 1/4, and so on. Okay, and then that is a new sequence. And then where is the limit of that sequence? And with that is to be determined. Similarly, the other sequence we continue on the right. Then once again, it is done recursively, one step at a time, creating a new sequence, defined nothing but recursively. So at this point, we do not have a formula for Pn as convenient as it is for the first one. So it is right there. Well, the point I'm making. Our original sequence has a specific explicit formula for it, and the new sequence, even though we can compute it step by step, we cannot evaluate it by just plugging in n. Okay, so that's if we take the formula 1 over n, you can plug it in at every time and I have my sequence. With Pn, I don't know what this is. So after n steps, where am I? I know that I'm 1 over n here. Where I'm here, I don't know. And that is the challenge. So limit of a sequence when given explicitly is fairly straightforward. 1 over n goes to infinity. Where does 1 over n go? It goes to 0. Okay, so easy. When you do summation, even though you know that every time you add 1 over n, which is going towards 0, doesn't mean that the whole thing goes into any particular place that we can guess. Same here. So 1 over 2 to the n, 1 over 2 to the n. It's easy. We have an explicit formula. Here we do not have an explicit formula. Without an explicit formula, we cannot substitute our we cannot just take what we know about limits in principle in order to find what it is. So that is the challenge. And so at best we can do what we did here with we do it numerically. So I have the two sequences here. This is 1 over n. This sequence, I believe, 1 over n. No, this is 1 over n. Okay. Let me. I hope you can see the whole thing there. N's, 1 over n's here, and this is the sequence of partial sums. So as you can see, I'm adding the next element. So you can see it right here. I'm taking the blue element above the previous element of the sequence, and I add the red element to the left in the red. Okay, and that way it is growing higher and higher. So as you can see, even though the sequence itself is and the original sequence is going towards 0 pretty fast, the summation, the series, the new sequence of partial sums, the third column, is growing even though very slowly. So the experiment was made last time to see where it's going, and we did quite a bit, and even though it seems to be slowing down significantly, it is, however, will be demonstrated not to converge. So that sequence diverges really slowly. You can see that this one on the right, the geometric series is what's on the right, so we have a geometric sequence here, multiplication. Every time we divide by half, roughly speaking, and then when that element is added, that sequence going to 0 so quickly that this sequence converges to 1 very quickly as well. So 1/2 plus 1/4 plus 1/8 is in fact, it gives us 1 eventually. Okay, but let me try to plot the bigger picture with as many elements as we can handle. So scatter, where's my scatter? Where's my scatter? Okay, 700, over 700 elements added. That's the x-axis, and as you can see, it grows first fast, and then it appears to be slowing down, and it does if you can imagine that it might be actually flattening out, and it is flattening out because it's slowing down in growth, so it seems to be slowing down, but actually it is going to infinity, even though after 700 steps we only have reached barely 7. Okay, so you can add, you can experiment with that, and that only will become more and more pronounced. In the meantime, if I carry out the same plan for this sequence, for the geometric series, this one, I do the same thing, and where is this thing? Here it is. Okay, I need more data, probably. If I want to have as many elements, so 726 steps. Okay, so you see the one on the right. This one is quite a picture. It grows and then flattens out right away. Pictures certainly do not prove anything, but certainly suggestive that it is going towards 0. Okay, so that's at this point. Best we can do is to experiment with the numbers and guess what the limits might be, including divergence. Even though this one is certainly it is inconclusive. I don't think you can draw any conclusion based on nothing but data. So we'll have to do analysis, full-fledged analysis, and to find out what the answer is. Okay, so one example I want to go back to from before. It takes slightly different flavor, but decimals, decimal representations. So you can think of decimal representations of numbers as sequences. We talked about that last time, but we can also interpret them as series. So here it is. An is equal to 0.9. I'm sorry. A1 is 0.9. A2 is equal to 0.09, and A3 is 0.009, and on and on. So AN will have n zeros, and n minus 1 zeros, and 9 at the end. Okay, so that is my sequence. If I start to now to add these together, so series, I form a series, partial sums. So P2 will be, I am adding the two previous ones, so it will be 0.99. I add 0.0009 to this number, so P3 will be 0.999, and on. So Pn, after n steps like that, there will be n nines. That's the partial sequence. Okay, so by design, it is a sequence that can be evaluated, but in general, we certainly do not expect it. This is just an example of what can happen, and we know that this one is going towards 1. That's a sequence, but by design, it is its behavior is predictable. So in other words, this is how I can write it up. I could write what? 0.999, what is the meaning of the, I could write it as a series like this. Summation 9 times 10 negative k. K from 1 to n. Well, then I can actually take n out, but, well, you can see what's happening. Maybe I jumped too quickly. Let me write it out. So it is equal to the sum of these, 0.9 plus 0.09 plus 0.009. And then you have a bunch of zeros. Okay, so it is an infinite sequence, and it's still to be explained why. Well, it seems to be convergent, so we are okay here. But I want to point out that we could, if we could, that's what we would like to do. Is if you really want to do algebra with these numbers, you might try to factor n out like this. So with 0.1 plus 0.01 plus 0.001. And then you have a bunch of zeros ending with 1, and there are infinitely many of them. And then that gives me a different representation of this thing. So the infinite decimals we can do algebra with infinite decimals. We have to, because if we want to deal with the decimal representation to begin with, which includes now not only the real numbers, so real numbers are irrational numbers, they have inevitably infinite representations, but also some rational numbers also have infinite representations, such as this one. 1/3 is all 3 through 3, and so on. So those repetitive decimal representations, the question is, if they are represented that way, can we do algebra with them? And the answer is yes, we can. If they converge, then we're okay. We will demonstrate that the algebra of series has the same properties as the algebra of sequences, and we can do algebra with them. Just enough said for now. Okay, so as I mentioned, the notation is also the sigma notation. So if I say A1 plus A2, AN plus, I can also write it like this, k from 1 to infinity, a k. Okay, so as if there are infinitely many terms put together, added together, but the reality is still the same. So every time you see this, if you can use theorems which you're going to prove, to do algebra with these expressions in calculus as well, that's all fine, but what's behind it is always the same thing. This is the limit of a sequence of partial sums. So this is, let me write it out, what this meaning of what meaning of this is. So it is equal, in fact, behind this notation, what is the limit of a k from 1 to n. Okay, this is what the meaning is. So these are partial sums. So in other words, summation goes up to n. That's it. So and then which creates a new sequence, and that sequence is then and then the limit of that sequence is taken if it exists. It might not exist. It's very easy to think of an example when it does not, and that an is equal to 1, right? You add infinitely many ones, and what do you end up with is infinity. Okay, so it is to be expected. And then there are certainly the different types of divergence. This one goes to infinity, but you can the one that we looked at earlier last week, the summation of -1 to the n. This one will be going up and down, and you can say that simply this one we say diverges. So the language is the same as for sequences, which adds to the confusion. But if there is somewhere, or if there is a word series present, then you should know that it's not a sequence, and there is more to it. Well, actually, there is, to illustrate this picture, I hope you may have seen this, I hope you can recognize something that you've seen not a long time ago, and there is certain analogy. So you add things up, and then more and more, and then take the limit of that process. So let me show you that picture. Let's see, where's the thing? Here it is. Okay, so does this, the top picture, look at the top picture, does it look familiar? The top row, what is it about?
Find an area under a graph.
Yes, and so look at how it expands to the right. Remember what this is about? So not one area, but the area expands, becomes longer and longer towards infinity. What do we call that? It's called improper integrals. And we are after the area under the graph, but the area under the graph is infinite. It is unbounded into infinity. So we do not stop anywhere. We want to know the whole area under the whole graph all the way to the right, to the infinity. So how do we do it? We compute the area on a shorter interval, and then we expand, creates a sequence, and then we take the limit of that sequence. Okay, so that's how we compute improper integrals over regions unbounded to the right. So it's the domain of integration for that integral is array from some number, say 0 on the left, or whatever that number is, and all the way this way, like this. Okay, so that's the domain of integration. So similarly, the similarity is actually striking here. We are also adding elements, except we imagine that our function is a step function. Okay, so one at a time it goes up and down, or you steps going down. But it is a step function, so it's made of horizontal pieces. And then once again we can ask ourselves what the area is, and how do we do it? We just nothing special about it. It's easier than the previous one because there is no integration, because the function is so much simpler. You just add one bar at a time. Add one bar at a time. It expands, makes it longer and longer and longer, and then you take the limit. Okay, so and that limit is the series. So in other words, what I'm talking about here. This is each of these is a sequence, a sub n, say, okay, and then once you add it together, so let's say maybe this is a n, then the whole thing is a partial sum. Okay, and then you have a sequence of partial sums, getting bigger and bigger and bigger, and then you take the limit. But so like this. In either case, we're expanding and taking the limit. Okay, so so what else do we need to mention about this idea? Is this is the theorem that came up before. Now we are just recycling it. There can be only one limit. There can be only one limit, and therefore only one sum of a series. Because the sum of a series is a limit, and limits, there can be only one limit. So we are covered here. We can use the word the because there can be only one. Okay. So you cannot converge to two separate numbers. Okay, so let's take a look at some more examples. examples of series, and all examples are based on the same. They are based on examples of sequences. So examples of series, but where they come from, they never come as series. They come as sequences. So they come from sequences. So the simplest one is constant. So say an is equal to a. If I go with partial sums, then what's going to happen is P1 is equal to a, P2 is equal to a plus a is equal to 2a, P3 is equal to P2 plus a, which is 3a, and then 4a, and so on. And the whole thing is going to 0 as long as a is not equal to 0. So unless it's made of zeros, it will go to infinity. Okay, one or the other infinity. So that's a constant sequence gives you a growing series, I'm sorry, not 0 infinity over here. It is very much like integration once again. So if you have a constant function, you integrate it, what do you get? You get a linear function that goes to infinity, unless it's 0. Okay? If you start with a linear function, you end up with a quadratic, and so on. So the similarity is there, and it is not coincidental. So number 2 sequence that also we have seen, it is arithmetic progression. So an is equal to an plus 1 is equal to an plus m. Okay, so once again, every time, as far as the sequence is concerned, you adding one amount at a time, the same amount at a time. So that is recursive, which it might be a little bit confusing if you do recursive for the sequence and then you use again it for the series. The series is inevitably, this is recursive, right? So we cannot get around that. So it is better than to use the explicit or direct formula. Fortunately, we have a direct formula for the arithmetic progression. An is equal to a naught plus mn. Okay, so how many times have I added m? And the answer is n, so I multiply n by n, and that's my formula. But that is now, we're moving on to series. So every time I add m, every time mn is being added, and then once again, if m is not equal to 0, what's going to happen? If m is not equal to 0, then I have p n plus 1 is equal to p n plus a n, which is p n plus a naught plus m n. And then once again, if m is not equal to 0, this thing will go to infinity. We're adding more and more. So it doesn't matter how small number m is, you will, when you multiply by n enough times, it will go to infinity. It is the geometric series that is interesting. The second one we discussed here. So the second one, as you can see, it converges so quickly. So you can justify it. You can actually justify this one, y is equal to 1, fairly easily. So let me try once again geometric progression versus geometric series. But first, geometric progression, which is a sequence. So I have an plus 1 is equal to an times r. R is the ratio. The idea is the same as the compounded interest or population growth, radioactive decay, or whatever the examples you might remember. The formula is very simple for, in addition to the recursive formula, we have an explicit formula, so it will be a naught r to the n. So that is the exponential growth for you. Okay, but then we might more want to add them together to create a series. So once again, these are the sequences, or the sequence, just given in two different ways: recursive and explicit. Recursive and direct, and then the series. we start adding them together. So Pn is equal to Pn plus 1 is equal to Pn plus An. Okay, so that number, remember, well, I guess I should, before moving on, I have to refresh your memory about where this one is going. And multiplication, consecutive multiplication, might lead you to infinity when if r is larger than 1. Okay, but it can also go to 0 if r is less than, absolute value is less than 1. Okay, so you multiply by smaller and smaller number, and that is the example of what we just saw. R is equal to 1/2, right? So you multiply by 1/2 every time, so you will have, and say A naught is equal to 1, 1. Well, let's say A1 is equal to 1/2. A1 is equal to 1/2. A2 is equal to 1/4. A3 is equal to 1/8, and so on. That's a geometric series. 1 over 2 to the n, on and on. So that's not a series just yet. It is the progression or sequence. Now, if I start adding these together, that's where the series starts. So this is the series. This is the sequence. And so that's just the, I put it in a row. I put that I have in a spreadsheet. So this is the y ends up with 1. Here's an explanation. I just take a square and I can cut it into smaller and smaller pieces like this. 1/2, 1/4, 1/8, 1/16, 1/32, and so on. Okay, so that's roughly, you can justify why the total area is equal to 1. So then the sum will add up to 1 as well. So certainly not approved, but at least it is a suggestion, a geometric evidence to the fact that the sum of the series. So once again, 1/2 plus 1/4 plus 1/8 plus 1 over 2 to the n, and if you continue to infinity, you will end up with 1. Okay, so that's the result that this picture is supposed to suggest. You can do a lot of similar things, but it doesn't work out as easily. So, for example, if you try to divide 1/3 plus 1/3 plus 1/3, it's not going to work out as easily. So that's why we need a theorem here. We need actual proof of what the sum is. The sum of the geometric series. Where is my geometric series? So there's a formula. Let me just find that formula. Okay, well, let's just start with the series. So geometric series with ratio r. Okay, so I'm writing the sequence just as I did, and then I put pluses between them. Okay, so here how it goes. So it will be a naught times r, a naught times r squared, a naught times r cubed, and on, a naught rn. Okay, so that is my sequence. Starts with 0, and now I put pluses between them, like this. And so that makes it a series. Without it, it's just a sequence. So series versus sequence. Okay. Now I have to. Well, it is meant to continue on indefinitely with the summation. So the trick to find the sum is to do some interesting algebra. What you do is So this is, well, let's do the partial sums. Now let me start over. So what is it equal to is the question. Okay, how do we find? Let's do it the right way, and the right way is not try to deal with infinitely many terms. So remember that, once again, that picture of the danger of having infinitely many terms added together in an arbitrary way. The order then would matter, and the result might not be satisfying. So that's why we're going to try here to do it carefully, and carefully means that we're going to use partial sums. To find the sum, use the partial sums, followed by the limit. Okay, so I'm writing then Pn is equal to a naught plus a naught r plus a naught r squared plus a naught rn. So it ends with a naught rn. Okay, now I multiply this by r. So I just take that expression, which is there is no trouble there, no hidden trouble, because it's just n terms added together. That dot 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 is only problem with dot 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 in the middle is that we do not know how to carry out that addition. It's not the problem with possible infinity. So we're trying to resolve that issue. So what do we do? We want to find an explicit formula to replace the recursive formula. Okay, so and that's the trick to cancel things. So I multiply everything by r. So r a naught, well, r a naught or a naught r. The next one, so the power of r increases by 1. A naught r squared plus a naught r cubed plus a naught r n plus 1. Well, maybe I'll do a bit more here. I need one more term here. So do a naught r n minus 1, a naught r n. Okay. So the trick is now to subtract and to cancel things. So if I start subtracting, first of all, on the left I'm going to have mpn minus rpn. Okay, and what here I'm starting adding things up, and I will cancel it. So here it is. This is gone. A naught r is gone. A naught r squared is gone, and they will be always canceling diagonally. I will be canceling two terms because of the subtraction, and this will be gone too, and this is gone too, and I'm left with only two terms. Okay, so then it is a naught plus a naught r n plus 1. And, well, that does it pretty much, because now I just solve it. I solve for Pn, the partial sums that we're interested in. Okay, so Pn then I have on left, I have a Pn 1 minus r equal to a naught plus a, well, let's factor out a naught 2, a naught 1 plus r n plus 1. Okay, and now I have Pn is equal to a naught 1 plus r n plus 1 over 1 minus r. I'm sorry, it is not a plus, it is a minus. This one. Okay. So that is the explicit formula for the partial sums. I might remind you that something like that happened in the late calculus 1 when you did Riemann sums. Remember Riemann sums? And then you would end up with a similar expression with dot 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 in the middle, and then you were supposed to take the limit of it in order to end up with a Riemann integral. Okay, then you remember those delta x's go to 0, and that is the limit. This is a slightly different limit, but the idea is the same. You have to convert your expression with dots to an explicit expression in order to be able to take its limit. So, okay, we have, and now the limit is fairly uncomplicated. So the limit is supposed to go to, where does the, on the right, where does it go? And the answer, it all depends. It will depend on R. The limit of this thing depends on R, but you can see certainly that to begin with we should probably require R not equal to 1. R not equal to 1, why we're not concerned with R equal to 1? Because then we are adding the same exact amount every time, and once again then we are in the place we're in would be the arithmetic progression. So it's not big loss if we require R not equal to 1. So we don't divide by R. But what about the numerator? It could, once again, we are in pretty much the same place. We have to make sure that the numerator does not diverge. Okay? So so once again, concentrate on this expression. The rest does not depend on n. So this is the only place that can ruin everything, the numerator. So when does it diverge? Well, in fact, why do we even worry about 1? This is the expression. This is the only expression that might create trouble. So R multiplied by itself infinitely many times. So what can happen? When does it converge? When does it diverge? As a sequence. So once again, series have been taken care of. That summation has been taken care of, and all the summation has been cancelled. We have a formula, Rn plus 1. It might go to different places. It might converge, it might diverge. So when does it diverge? What value of R might cause it to diverge? R is greater than 1. Yeah, R is greater than 1. Rn plus 1 will go, R greater than 1 will go to infinity. To infinity as n goes to infinity. Okay? In fact, so once again, this is actually just an example of a geometric progression. So what we know about geometric sequences can be applied. So if R is less than -1, we're pretty much in the same place. Only, well, it might be worse, because this one, if you have a number that is a negative and you keep multiplying by itself, not only it goes to infinity, it also alternates signs. So instead of going like this to infinity, it goes like this. So it goes to both infinities at the same time, so which is really bad. So doesn't matter, it diverges. It badly diverges, so we just throw it out. And then we're left with what we're left with. So we threw this out, in that one and this one. The one that remains is, well, -1 is just as bad. So -1, we end up with a sequence alternating between -1 and 1, and once again it diverges. So we're left with R only between -1 and 1. So if R is absolute value of R is less than 1, then we have convergence, and in fact that expression goes to, so R is less than 1, then Rn plus 1 goes to 0 as n goes to infinity, because you multiply by a small and small number. So and that works out perfectly for us, because now we have a formula. On the right I have, well, it's gone, I have simply A naught divided by 1 minus R, a really simple formula for what? For the sum of our series. So this is the sum, A naught Rn plus 1, Rn, n from 1 to infinity. And it gives us a very simple formula under this restriction. So if you want to look at the whole thing, this is our conclusion. So if the absolute value of the ratio is less than 1, then the series converges. We did it honestly, precisely, using the partial sums, evaluating the limit, and we have a formula. So for geometric progression in that sense is the simplest series that actually produces results that are kind of interesting in comparison to arithmetic progression, which causes either pretty much diverge almost all the time. But this one, as you can see, has a formula, and it's pretty interesting. And we can confirm that if A naught is equal to 1/2 and R is equal to 1/2, that is the previous example. Then what do we have? The sum is equal to 1/2 divided by 1 minus 1/2, which is 1. Okay, so it adds up to 1. Okay. On the other hand, if I pick, say, A naught is equal to 1 and R is equal to 1/3. So in other words, I'm talking about 1 plus 1/3 plus 1/9 plus 1/27 and so on. What does it add up to? And we have taken care of that. We just plug it into the formula. I have 1 divided 1 by 1 minus 1/3, and the answer is 1 over 2/3, 3/2. So this thing is equal to 3/2. Okay. So any geometric progression then can be evaluated very, very simply. I do want to state the theorem in its entirety so that we could also have the statement about the divergence as well. So the theorem is so the geometric progression with A naught not equal to 0 converges if and only if the ratio is less than 1, absolute value, and in that case, and then there's a formula. The summation A naught Rn, and from 1 to infinity is equal to A naught 1 minus R. So the formula is misleading a little bit because it is actually makes sense even if R is larger than 1. So you can try to plug in R equal 2 into the formula, it will work out, but you know it's simply the series diverges. So so for example, it's 1 plus 2 plus 4 plus 8. So do not try to apply the formula at the bottom to this series because it will produce a number, and yet it's cannot possibly be a correct number because this one diverges. So just a warning, and then it is as it is frequently the case is the restrictions of the theorem are very important, and they indicate the applicability of your result. Okay, so so the geometric series, we can certainly take this one up and confirm that the result that would be uncomplicated if I take this one geometric series, and then if I plug in here, I start with over here. I start with 1, and then I go 1/3 1, and then I divide. I will go to 3. No, wait a minute. 3, and here I have 1/3 to the power. Oh, it doesn't matter. Okay, so we start with 1, and then no, actually, it doesn't matter. I'm afraid. Let's do it this way. Okay, 1/3, 1/9, and so on. So let's see what it adds up to confirm our formula. Down. What happened here? I don't know what happened. I don't get it. Okay, so at some point, what happened? At some point, things. Well, you know, it happens sometimes with computers. You see what happened. It's the same formula, right? So there is nothing wrong with the formula, but the formula is, as you can see, the formula is I divide 1 by 3 to the power of 652. So, you see what happened? Anybody familiar with how computers operate?
It started estimating it to zero.
Yeah, it thinks that that number, that power is the power of that number is too large, and when and then it cannot handle it pretty much. It's just the number is just too. Yeah, it thinks it's infinity. It thinks the denominator is infinity, and the computer cannot divide by infinity. It is just not the operation that it carry out. But there's a trick. Well, at least I think it might be able to get around it if we try to, instead of dividing 1 to this power, 1 divided by 3 to this power. How about we take 1/3 to this power? Which should be the same. Algebraically, it's the same thing. But what I wonder what the computer is going to say. Okay, so different. It sees differently. So 1/3, it doesn't have to deal with infinity anymore because the number is just simply very small. 1/3, it converts 1/3 to the decimals, roughly speaking, and then take it to the higher power, and then everything goes to 0, right? So as you can see, that works out, and the graph is right there. It is, what does it give? It gives me one. Why does it give me 1/2? Okay, 1/2, starting in 1/3 plus 1/2. So the case I considered was slightly different, but so this is the difference. So if I start with 1, I get 3/2. I start with 1/3, I will get 1/2. Okay, so everything is fine. Okay, so let me wrap this up. So next I'm going to do the other series. So that series now requires series intention because it is divergent in this kind of interesting way. Anyway, so okay, so we'll just